members. We also have quite a few people who sign up online. So that's great to hear so much interest what we're doing. And as Scott mentioned, so I'd like to introduce you to what Quantemol is actually doing. And probably the best way to do it is to give a little case study, short case study, where I will demonstrate how products we have, how we use them in-house for our consultancies. So as a company, we have products, but we also offer consultancy services where we use our own products. So that's
yeah.
So a few words about Quantemol. So first of all, we have three main products. One of them is Quantemol EC, electron collisions. So this is a software to provide you electron molecule scattering cross sections. Another one is Quantemol VT, virtual tool. So this is an expert system, user-friendly interface around hybrid plasma equipment model, HPEM, developed by Professor Mark Kushner, who will speak after me. And last but not least is a Quantemol DB. It's a plasma chemistry database. So this is a database with goal to provide you all information you need to proceed with your plasma modeling, or almost all. And it's free to sign up, free to download data. But it also has paid membership, and paid members have some additional services, such as one of them became a global model app, where we have additional functionalities for processing plasma chemistry data. And let me give you a project example. So usually companies approach us with some unusual mixed gas mixture or something. One of the components of the gas mixture will be some quirky molecule. And the goal of plasma modeling in this case will be to understand the nature, the difference maybe from traditional chemistry mixtures, or how to, let's say, increase certain radical in this plasma mixture using some macroscopic parameters you can manipulate in the reactor. And actually later Peter Wenzik will talk with us about demands of plasma disposition. So what do we do? So Quantemol's workflow consists of 5 steps. So first of all, of course, it's chemistry assembly, see what's out there. Then we identify missing reactions and missing data. And the third step will be filling in the gaps where we can and how we can. And the fourth step will be putting it all together, ensuring the chemistry is self-consistent. And the fifth step will be addressing the surface chemistry interactions. So let me walk you through these steps. First of all, of course, we turn to our own database when we look for a gas mixture. And the data there is from open source. And also, as I mentioned, anyone can sign up, download the data. So, and if you work to collect some reactions, they're very user-friendly interface how you can search for reactions. You can specify the type of reaction and so on. However, if you are a paid member, then you get access to this Quantemol global model. And this is a software, it's a desktop software, but it's connected by API to the database. So it needs to be installed on a computer with internet. And there are a couple of options you can use. So one of them is assembling chemistry set for you. So all you need to do is, let's say, tick boxes which are your feedstock gases and tell the software how many steps of search you want it to perform. In the first step, it will look for all reactions which have your feedstock gases as reactants. In the next step, it will look for all the kind of reactions which contain the products from the previous step as reactants, and so on and so on. So if there is data, you can get quite a comprehensive set in a few steps. And then the alternative option also, we have a library of pre-assembled chemistry sets. So you can look into them and maybe choose one which can be a starting point for modification. So, and then once you have collected data from the database, then we enable some consistency checks. So this is just flags for you. So you are aware that maybe you're missing some important processes. So you can bypass them and carry on running simulation, but we'd recommend to consider them. And after that, so essentially, I would classify the types of missing information in three. So first of all, very important, electron molecule scattering data. So electron collisions are driving plasmas. It's very important to have accurate data in this domain. There's also, of course, lack of data very often in heavy particle collisions and cross sections, as well as species properties, and sometimes overlooked, but nevertheless very important. So, and how do we approach each of this? So for electron scattering, we're actually uniquely positioned in the sense that we have a software which is ab initio, and the only input for it will be molecular formula or molecular geometry, and then it can generate electron molecular scattering cross sections. Initially, the main base model was UKRMO Plus, but now it has expanded to include different models, including, for example, vibrational excitation, which is a model which was developed actually by Professor Kakulin, who will speak later on today. But now it's also included in Quantemol, and people can benefit from vibrational excitations. However, so and the processes I've listed here, so they pretty much can be imported in your plasma modeling software. They don't need much changes. However, there are a couple of processes which are not so easy to import, so that's why there is no direct link yet between QDB and QC. And one of them is electronic excitation, because there are essentially two potential pathways. So your excited molecule either will be non-dissociative, and in this case, you can include it explicitly in your chemistry set, or you can assemble them in pooled states, which is often the case in plasma chemistry, so you have less species with limited information in the plasma chemistry. But also the very critical process dissociative, then we need to estimate branching ratios. So I'll get back to you in a couple of slides to this. And another process is ionization. So dissociative ionization, again, the software will calculate your total cross-section, but the branching ratios need to be identified. So we have developed a model for identifying branching ratios using mass spec data. However, there are limitations like how much mass spec data available. For example, I'm showing here the mass spec of caffeine. I don't know many plasmas running on caffeine, and plasma physicists do. But, so what do you do if you don't have a mass spec? And sometimes it's not even possible to measure. So there we have actually developed a machine learning model for estimating mass spec, and there was a publication actually which came out recently. And I want to also mention that this is not just a black box machine learning model, because the data in this domain is scarce. So my colleague Katarina Limishka, so she was doing a very bespoke model, taking into account the types of molecules, types of processes. So it's a kind of hybrid between machine learning and also understanding physics. And as a result, it's a reasonably accurate model, which we use in practice quite a lot. So on the left here, so this is an example of just validating our machine learning model. Branching ratios estimator. So the experimental data is in dashes, and the solid lines are the calculated ones. So comparison is very good. And on the right, so this is the actual molecule where you wouldn't be able to get this data. So, however, using our machine learning model, we estimated first the mass spec and then the branching ratios for this section. So we use it in simulation. So, and let's get back to the neutral dissociation branching ratio. So this is very often, like this is one of the features very much in demand from customers. That wants to know how their precursors break up. So, and there are three essentially approaches how to deal with this problem. So one of them, which we very often use, is analyze potential energy curves. So it's very much expert driven. So it's qualitative, and it depends on the person who's doing it, the experience they have, the knowledge. And then they essentially will look at the shape of molecular orbitals, energy curves, and they will suggest what branches are likely to break up. However, it's less than ideal for very large molecules because there are many options there. And we have established collaboration now with Leeds University, who already had pre-existing methods that we're using elsewhere, but actually turned out to be applicable for this case as well. So they use molecular dynamic method, and they can calculate branching ratios for these molecules. So we published this paper last year, so welcome to read more about the method here. The disadvantage of this method that it takes a little while, and it's computationally demanding, at least at the moment. However, the further kind of like outcome of this collaboration is that we together work to develop rules, how kind of like what makes the breakup more likely based on this work. And this is the paper. Our paper actually was just accepted. Ryan, the domain author Ryan is here, so let us know, we can introduce you to him if you're interested. And we can, I guess, this method can enhance our analytical approach and be also fast, but also based on calculations. And my colleague Oliver Brumley will speak later today and present some results of Quantemol calculations. Then we move to the domain of heavy particle collisions. So this is, information very often is scarce. Again, we developed a machine learning model, and this is available on QDB website. So anyone who signs up for free is very welcome to use it. So this is for collision of two neutrals producing two products. And in addition, often customers ask us for charge exchange data. So we have used, again, similar analytical model for Quantemol, and this is available in our global model hub. The next step is diffusion coefficients estimator. Again, we have a machine learning model for that. So this is available for all Platinum membership users. And we are kind of like in the process of preparing release for ion mobilities estimator as well. And so hoping that all can help to assemble chemistry together. So once we assembled all this reaction, all of this data, so we can quickly run simulations in our global model to ensure the chemistry is self-consistent. But additionally, the additional functionality of it is also there is something called species ranking. So the software can help you to identify, for let's say your species formation, like CO2 in this case, what are the critical species for its formation if we rank them. And you see that F2 is more important than COF, for example. So that's a help in case if you're working with a tricky molecule and you want some particular, let's say, breakup product. Or another aspect is what we can do is chemistry optimization. So this is the way the software will kind of, with your fixed parameters, it will suggest you what species can be removed from the set in order for you to kind of remain within the same boundaries you want for desired species. Let's just maybe better show them an example. So we took this example, the paper 42 species for N2H2 chemistry. And we, of course, we're fixing here the process parameters, and we identify species of interest NH, NH2, NH3. So we ran our optimizer, and we were able to reduce it to 19 species, more than a half, which will, will cheer up people who can want to take this chemistry to 2D and make it faster. Key and last but not least, so the information on surface chemistry is very scarce, and of course it's also variable, sometimes reactor to reactor and so on. So the solution which we discussed with our clients and was inspired by clients' demand is actually provide like a fitting ability to fit data. So if they have experimental data, we can fit surface coefficients with that data as best as possible. And also we can vary if there is no data, but they want to see the impact on the bulk plasma of various variation if it's in coefficients, then that can be done. And yeah, so that's kind of like more or less where consultancy part concludes. And just a couple of slides. So one about our future developments and the collaborations we will fostering is, so we work on collisional radiative model, and the goal would be to model optical emission spectra. So, and what we want to establish is a link between what you see in experimenting industrial reactor you can get OES from, and try to compare it with your model to validate the chemistry. And also additionally, you will be able to calculate the amount of UV radiation. And this development was also enabled by us collaborating with UCL, that they produced this database, which is an important input for that model. And more recent developments, which my colleagues will talk about today, is machine learning model sputtering. Well, I guess maybe Catherine won't talk about it today, but you'll see it in our release soon. So it's for polyatomic targets. And also she will present a talk about initial species density estimations for plasma model for hydrofluorocarbons. And the next also very interesting development is effective core potentials. So this is the project we worked on together with Charles University. So they implemented the approach in UKRMO Plus, and we've implemented that in QC. So now there is a capability to calculate cross sections for molecules with heavy atoms like tungsten, gallium, and so on. So please speak with Katarina and Greg if you're interested, and they will both present later. And yeah, so this is the end of my talk. Thank you very much for listening, and thanks to everyone who actually worked on this and work I have presented. If you have technical questions, I put Sebastian's on the pictures here, so you can comment. And thanks again.